Have you ever found yourself just like staring at a growing stack of articles or maybe research papers, or even just a mountain of unread emails? You know there's vital information hiding in there, but you just feel completely overwhelmed by the sheer volume.
Oh, absolutely.
You want the essence, right? The core insights, and you need them fast without having to slog through every single word. If that sounds familiar, then you are definitely in the right place.
Yeah, that feeling of information overload,
Hmm.
um, that's precisely why we created the deep dive. This
Well,
isn't just another show. It's meant to be your personalized shortcut to becoming genuinely well-informed, quickly and thoroughly.
hmm
And today we're diving headfirst into a topic that's really shaking things up in the world of web development,
yeah.
Angular signals.
I'm genuinely excited for this one. You've provided us with just a fantastic collection of sources for this deep dive. It's like a treasure trove of insights. It covers everything from the foundational principles of reactive programming all the way to the nitty-gritty of the core Signal API. How computed signals derive smart data, the crucial role of effects in managing side effects, and ultimately how it all comes together for robust state management and incredible performance. It really feels like Angular signals are designed to tackle some long-standing developer pain points.
Absolutely. And our mission today is basically to unpack all of that for you and hopefully demystify any lingering questions. We're going to break down exactly what signals are, how they function at a fundamental level, and maybe most importantly, why they represent such a significant leap forward for building high-performance, maintainable applications.
Okay, so we'll simplify some, truly complex concepts, walk you through practical examples, and really connect all the dots. So you're not just understanding what they are, but why they truly matter to your development workflow. So if you're sitting there wondering, okay, how do signals compare to what I already know about Angular's reactivity, maybe like RxJS, or how do these really make an application faster in a way that I can actually feel in my daily work? Then stick with us. We're going to cover all that and much, much more. Let's get into it.
Sounds good.
So let's maybe kick things off with the big picture. This reactive revolution we keep hearing about. What exactly is it, and where do signals fit into that whole landscape?
Right. Well, when we talk about reactive programming, we're essentially describing a declarative paradigm. It's all about designing your code around data streams and the propagation of change.
Propagation of change.
Okay. Think of it less as a sequence of instructions like do this, then do that, and more about expressing how your data flows, whether that data is static, like, say, users' initial preferences, or constantly changing, like livestock prices or readings from a sensor.
Right, like real-time stuff.
Exactly. Reactive programming automatically handles what happens when that data shifts. You just declare how your data relates, and the system takes care of all the updates without you needing to, micromanage them.
And the classic analogy here, the one that always clicks for me, is just a simple spreadsheet.
Oh, yeah. Perfect example.
Right. When you change a value in one cell, say cell A1, and other cells have formulas that depend on A1, like maybe B1 calculates A12, or C1 sums A1 and B1,
Wow.
those dependent cells update automatically. You don't have to manually go and recalculate B1 and C1, do you?
Nope. It just happens.
That's reactive programming right there. The changes just sort of ripple through the system.
Exactly. And that concept, that propagation of change, is absolutely key. When a value in one of these data streams changes, that change doesn't just sit there. It automatically propagates to all its consumers.
Okay.
And this is incredibly powerful because it eliminates the need for any manual updates on your part. It ensures that your application state is always consistent across the entire application, no matter where that data is being used.
So the consistency is sort of baked in. That must dramatically reduce the chance of, stale data showing up across the UI or something.
Well,
Like
exactly.
imagine a user updates their profile picture or maybe their email address. In a truly reactive system, those changes are instantly reflected throughout the application wherever that info is displayed. You don't have to manually refresh every single section or component showing the user's details. The system just knows to update because it's reacting to the change.
Precisely. And this isn't like a completely new concept in modern web development. Many contemporary UI frameworks, Angular, React, Vue.s, they already lean pretty heavily on reactive principles to manage UI updates. The core idea is simple. When the underlying application state changes, the UI automatically re-renders to reflect that new state, gives you a seamless user experience.
Okay, so that brings us to the star of our show today, signals. If reactive programming is this powerful foundation, then Angular signals are like a new fundamental building block within that paradigm. They're introduced as a new reactive primitive directly in Angular, representing values that change over time.
Yes, you can think of them as being, well, similar to variables, but with the added ability to notify consumers when their value changes. And that notification mechanism, that's the core enabling factor for building truly reactive applications where components and services just update themselves automatically whenever the data they depend on shifts. It's a very intentional design choice by the Angular team to provide more direct, synchronous, reactive primitive.
Okay, let's dig into the key characteristics then. What exactly makes signals so special beyond just being a variable that notifies? First off, the sources mention fine-grained reactivity. This sounds like a huge deal. It means signals enable very precise change detection. So instead of Angular having to broadly check large parts of your application for changes with signals, it only updates the exact parts of the application that depend on a specific signal. How big a shift is that really in practice?
Oh, it's colossal. It's a colossal efficiency gain. And honestly, it's a bit of a game changer. To use your earlier analogy, imagine that complex machine with all the interconnected gears. In a traditional system, if one gear moves, you might have to check every single gear in the whole machine just to be sure everything's in sync.
Right, check everything just in case.
Fine-grained reactivity means the system only checks the specific gears that are directly connected to the moving part, and then only the next set connected to those, and so on. It's surgical, not broad. And this isn't just some minor optimization, it's a fundamental shift. It can free you from that traditional, Angular change detection dance of agonizing over on-push components and zone.js concerns.
Yeah, I know that dance.
It means Angular is now doing the heavy lifting you used to spend precious development time optimizing yourself, letting you focus more on the business logic, not the framework internals.
Wow, that really puts it into perspective. And how does it know which gears to check or which parts of the UI to update? That must bring us to dependency tracking.
Exactly.
Signals automatically track which components and services are actually using their value. Is this the magic that allows them to efficiently notify only the interested consumers?
Precisely. Angular doesn't just read the value when you call some signal. It actually understands that this is a signal and sets up this kind of invisible wire or a connection behind the scenes. When you access some signal within a template or a computed signal or an effect, Angular registers that this specific piece of code now depends on some signal.
Okay.
So if some signal changes later, Angular knows exactly which bits of your template or which computed signals need to re-render or reevaluate. It's a beautifully simple yet really powerful mechanism.
And one more crucial characteristic you highlighted, synchronous updates. When a signal's value is changed, that update happens immediately, synchronously. What's the benefit there?
Well, this ensures that the application state is always consistent right after a change happens. You don't have to worry about race conditions or stale data lingering around between asynchronous operations. You change it and the new value is just there. Plus, the API itself is intentionally kept simple and intuitive, which makes signals easy to use and understand for developers, really flattening that learning curve.
Okay, so we've laid the groundwork for what signals are and why their characteristics are a big deal. Now, the natural question is, why should I as a developer actually care? What are the concrete, tangible benefits of actually embracing signals in my Angular apps?
Right. The first and probably most direct benefit is unequivocally improved performance. Because of that fine-grained change detection we just talked about, Angular needs to do significantly less work to update the UI.
Less work, better performance. Makes sense.
And this translates directly into better performance, especially in complex applications with frequently changing data. It's often not just theoretical. You'll likely feel the difference in responsiveness.
And who doesn't want faster applications, right? But beyond just raw speed, how do signals translate into maybe a better developer experience?
That's where simplified code comes in. For many common reactive scenarios, signals have a simpler API than RxJS observables, which often means your code becomes easier to read and understand. Less cognitive load for developers is always a win. While RxJS observables are fantastic for streams of events over time, often asynchronous, signals are really designed as a more synchronous, simpler primitive, especially for local synchronous state management. Think of them as complementing RxJS for many common UI reactivity patterns, rather than completely replacing it.
That sounds like a massive relief. I mean, I still remember the days of manually managing subscriptions and all that.
Absolutely. And that leads straight into reduced boilerplate. Signals eliminate the need for manual subscription management, which, as you know, is a common source of bugs and just verbose code when dealing with RxJS. You write less, and the system handles the cleanup automatically, preventing those dreaded memory leaks.
Okay, less cone, fewer leaks, and if something does go wrong.
Signals promise better debugging. They provide clear and predictable update paths. In the world of reactive applications, this can make tracking down issues much, much easier. No more chasing down elusive subscription chains through complex RxJS pipelines. It's just a more direct flow.
And where do they really shine? The sources highlighted some key use cases.
Yeah, they're incredibly versatile. For instance, component state management, they're ideal for handling the internal dynamic state of individual components. Very clean. And for sharing data between components reactively, they offer a powerful, efficient solution. Beyond that, they're excellent for building reactive forms, where inputs automatically update and react, and crucially, for optimizing change detection in complex Angular applications. It really feels like a fundamental building block that will underpin a lot of future Angular development, making common patterns significantly easier to implement.
Okay, now that we have a solid grasp of what signals are and why they're so beneficial, let's roll up our sleeves and look at the nuts and bolts. How do we actually put these signals to work in our code? How do we create them, read their values, and most importantly, update them?
All right, let's get practical. At the very foundation, we have the signal function. This is the fundamental building block. It's essentially a factory function that returns a new signal instance, which you can think of as just a special container for a reactive value.
And it looks incredibly simple to use, which is definitely part of its appeal. Like const count signal, that creates a signal named count with an initial value of 0. But the magic here, as we discussed, is that count isn't just a regular variable. It's a signal holding a numeric value. Any component or service that depends on it will automatically update when that value changes.
And what's fascinating is the versatility. Signals aren't limited to just numbers or simple types. They can hold values of any type, primitives like numbers, strings, booleans, but also complex objects and arrays. The type is usually inferred directly from the initial value you provide, making it very intuitive.
Okay.
So you could have signal John Doe for a string, signal false for a boolean, or even more complex types like signal string for an empty array of strings, or maybe signal name, string, age, dollar number for like a user object.
And it goes beyond simple direct values too, right? The sources said you can initialize a signal with the result of a function call. That sounds useful for dynamic initial states.
Exactly. For example, you could have const card items, signal initial card items, where initial card items might be a function simulating fetching data from local storage, or perhaps getting initial state from a configuration file. It means your initial state can be dynamically determined without blocking your component render.
That's neat.
Our sources even mention practical exercises like creating a message signal, hello signals, a price signal, 9.99, a products array signal initialized as an empty array of objects, and a last updated signal initialized with new date. This really shows how versatile signal initialization can be, handling diverse data types in dynamic setup.
Okay, so once you've created a signal, how do you actually get its value? Our sources mentioned using the get method, for example, const current count.get. But then they also noted that in templates, you just call the signal as a function. Like, what's the distinction there? That might trip people up.
That's a great question. And yeah, it can be a bit confusing initially. The get method basically returns the signal's current value without triggering any change detection directly. It's like a raw, immediate read. You might use it in places where you just need the value right now without setting up a reactive dependency.
Okay, just the value, no strings attached.
Right. However, when you use in your Angular templates, or maybe within a computed signal or an effect, Angular's template system does automatically understand that you're accessing a signal's value in a reactive context. It then sets up that invisible connection we talked about, ensuring the template or the compute effect updates when that signal changes.
Ah, so Angular's templating engine and the signal runtime are smart enough to know when to listen and when to just grab the value.
Precisely. And this mechanism of accessing a signal's value by calling it as a function is crucial for how it works within computed signals and effects.
Yeah.
When you access a signal's value within one of those contexts, Angular automatically tracks the dependency. This is how it knows to reevaluate the computed signal or rerun the effect whenever the source signal changes. You don't have to manually register listeners. It's all handled just by calling the signal like a function.
Got it. So we've created signals, we've read signals. Now, the final piece of the puzzle for core mechanics, how do we update their values? Our sources talk about set, update, and mutate. Let's start with set.
Okay, set is the most straightforward. It's used to overwrite the value of a signal entirely. When you call it with a new value, Angular notifies all subscribers. That means any components, computed signals, and effects that depend on it, that the signal's value has changed. Basic usage is simple, .count.set1,
Or
which just changes the signal's value to 1, completely replacing whatever was there before.
Now, this next point feels absolutely critical based on the source material set and immutability, especially for complex types like objects and arrays. It says you should create a new array object instead of modifying the existing one. Why is that so important? I feel like I've seen developers get tripped up on this kind of thing before.
Yeah, this is fundamental to predictable reactivity, and it's a common trap if you're not careful. Signals primarily track changes to the reference of the value they hold, not necessarily changes within that value if it's a complex type like an object or array.
Okay, the reference.
Right. So if you were to directly modify an array, say by doing items.get.push, orange, the item signal itself would still hold a reference to the exact same array object in memory. The signal wouldn't detect a change because its reference hasn't shifted, and therefore it wouldn't know to notify its dependents.
Ah, so the signal wouldn't know to tell anyone it changed, even though the array's contents did change. That would lead to stale UI for sure.
Exactly. The correct example from our sources is items.set.items.get. Here, you're using the spread operator to create a brand new array that includes all the old items plus the new orange. When you set this new array, the signal's reference does change, and it correctly notifies all its dependents. This adherence to immutability makes your code more predictable, easier to debug, and less prone to unexpected side effects, because you always have a clear new state. It's just cleaner. That makes perfect sense. Okay, what about update? It sounds like it's designed for scenarios where the new value kind of depends on the old one.
you're spot on. The update method is designed specifically to perform calculations based on the signal's current value. It takes a function as its argument, and that function receives the current value as its parameter. So count.update current count plus best one increments the count by 1. The key benefit here is that it ensures you're always working with the most up-to-date information, because the function receives the current signal value at the time of the update, preventing potential race conditions or using a stale value.
Okay, and then there's mutate. The source mentions using it with caution. What's the deal with mutate? This one always seems to come with a bit of a warning label.
Mutate allows you to modify the value within a signal without replacing the entire value.
Yep.
It's particularly useful, the sources say, for large, complex objects or arrays where creating a new copy would be inefficient. For instance, in a to-do list example provided, if you want to toggle the completed status of a specific to-do item, you could use todos.mutate. Current todo find it to do and update its completed status. You're directly modifying the to-do object inside the current todos array rather than creating a whole new array with modified objects.
So it's an in-place modification, and Angular is somehow aware of that change, even though the reference didn't technically change.
Correct. Angular is aware when mutate is used. But the source explicitly warns to use mutate with caution because it can make your code harder to reason about if not used carefully. My personal rule of thumb for choosing between setUpdate and mutate is this. Think of mutate as a surgical tool. Use it for very specific performance-critical hot paths with large data structures, and only when you've actually proven through profiling that recreating the object is a genuine bottleneck.
Okay.
For 99% of cases, immutability with set or update will lead to much more robust, readable, and debuggable code. It just simplifies the mental model of your application state significantly.
Okay, that decision framework is super helpful. Let's tie this all together with a quick practical application like that shopping cart scenario the source mentioned. Say you have a cart item signal, initialized as an empty string array. How would you handle adding items and updating counts using these methods?
Sure. So you'd define it maybe as cart items as signal string. To display the number of items in your template, you'd simply use cart items. That's the thing. If a user adds an item, you'd ideally use cart items.update, items new item, or cart items.set.cartitems.cartitems to ensure you're creating a new immutable array. That's the preferred approach for simplicity and predictability.
Right, stick to immutable first.
Exactly. Now, if you had a truly massive cart, like thousands of items, and you needed to update a property within a specific item in place, then mutate might be considered after profiling. But for most typical web applications, immutable updates with set or update are perfectly efficient and much safer, easier to reason about.
That makes a lot of sense, showing how set, update, and mutate each have their specific roles, with that strong preference for immutability whenever possible. This core mechanic really lays the groundwork for everything else we're going to talk about. Now that we understand the core mechanics of creating and updating signals, let's talk about smart derivations. Understanding computed signals. This feels like where signals really start to shine in terms of building intelligent reactive applications, where values automatically keep themselves up to date without us doing much work.
Absolutely. The core concept here is that a computed signal is a signal whose value is derived from one or more other signals. Think of it almost like a function that automatically reruns and updates its output whenever any of its inputs, those source signals, change. It's essentially your reactive calculation engine built right in.
So it's not just a calculation that runs once and stores a value, it's a reactive calculation. And the key is that when any of its source signals change, the computed signal is automatically reevaluated. That sounds like magic, but it's really just clever engineering saving us a lot of manual wiring, right?
It truly is clever. And creating them is straightforward using the computed function. The syntax is equally elegant. Computed takes a compute function as its argument. Inside this function, you access the values of other signals by calling them as functions, just like first name. And as we discussed, Angular automatically tracks these dependencies for you. It builds that invisible graph of what depends on what behind the scenes.
Let's run through some simple examples just to really nail this down. If you have a first name signal and a last name signal, you could have const full name computed.
Yeah.
Any change to first name or last name immediately updates full name. Simple, elegant, reactive.
Or for something numeric, if you have a side length signal, const area computed gives you a reactive area. You can also see how it works with multiple dependencies, like const discounted price computed, discount percentage number price. Change either the original price or the discount percentage, and discounted price instantly updates. The beauty is you don't write any code to explicitly listen for these changes. The computed signal just handles it.
Even conditional logic fits right in. Const is even computed to, computed to, Laro. This seems incredibly powerful for chaining calculations, too. The sources give a great example of shopping cart totals.
Right, the chaining is key.
You could have subtotal computed from item price and quantity, then discount amount computed from subtotal and discount percentage, and finally total cost computed from subtotal and discount amount. Changes to any base signal like item price would then ripple through this entire chain automatically, giving you an always accurate total without manual updates.
That chaining behavior is where the magic behind the scenes really becomes apparent. That automatic dependency tracking. You just write your compute function, access the signals you need, and Angular builds that dependency graph and handles the rest. It's all automatic.
And it's not just direct dependencies, is it? The source points out deep dependency tracking. Like if signal A depends on B and B depends on C, then A implicitly depends on C as well.
Correct. A change to C will correctly trigger reevaluations for both B and A. The example of final price depending on discounted price, which then depends on price and discount, clearly illustrates this. A change to the base price or discount will correctly reevaluate both discounted price and final price. This automated propagation simplifies your mental model enormously because you just declare the relationships, and the framework ensures everything stays consistent.
Now here's a crucial optimization point the source highlights. A signal is only tracked when read. What does that mean for efficiency? This sounds like it could prevent a lot of unnecessary work if used right.
It means exactly that. A signal is only considered a dependency if it's read within the computed function. If you define a signal somewhere but never actually access its value inside the compute function using signal name, changes to that unused signal won't trigger a reevaluation of your computed signal.
Ah, okay.
Our sources had a perfect illustration. An alert message computed signal depends on temperature and alert threshold, but not humidity, because humidity is never called inside the alert message's compute function. So if humidity changes, alert message doesn't waste time rerunning. This is a subtle but powerful built-in optimization for performance.
That's very clever. And what about conditional dependencies? Does the dependency tracking adjust if my logic inside the computed function changes which signals are actually being accessed at runtime?
Yes. This is another important optimization that really showcases the intelligence of the system. Dependencies can change dynamically based on the logic within the computed function. The example of temperature converting between Celsius and Fahrenheit based on an S Fahrenheit signal is key here. Both temperature Celsius and is Fahrenheit are tracked, but temperature Celsius is only used in the conversion when it's Fahrenheit is true.
Right.
Similarly, a display data signal might conditionally depend on detail data or summary data based on a show details signal. If show details is false and summary data is being used, a change to the unused detail data signal will not trigger reevaluation of display data. This dynamic dependency tracking is a significant performance gain for complex UIs, as you only pay the computation costs for the data paths that are actually active at that moment.
So speaking of performance, how do we actively optimize computed signals to make sure they're as efficient as possible beyond these built-in smarts.
Right. Well, the first rule for minimizing reevaluations is simply to avoid unnecessary dependencies. As we just discussed, only access the signals that are actually needed for the calculation. Don't bring in signals if their values aren't strictly part of the computation you're doing right there. Each signal read creates a dependency, so be intentional about it.
And then there's memoization, which our sources say is built in. That sounds like a big win, handling a common optimization problem automatically for us.
It is, and it's fantastic. Computed signals inherently provide memoization. This means they cache the results and avoid recalculating them if the dependencies haven't changed. So if you have an expensive calculation that relies on a data signal, it will only actually run the calculation once when data changes. Subsequent accesses to the computed signal will simply return the cached value instantly until data actually changes again. This is a huge performance booster, especially for calculations that might be complex or time-consuming.
Are there any potential pitfalls of memoization that a developer should still be aware of, even with this built-in feature?
Yes, there are a couple of nuances. For very large, complex objects or arrays, caching can potentially lead to increased memory usage if the cached values themselves are substantial. More importantly, equality checks are crucial. Memoization relies on comparing the previous and current dependency values to decide if recalculation is needed. For complex objects, the default equality check, which is usually reference equality, might not be what you want.
How so?
Well, if you replace an entire user object with a new object reference, the username computed signal will reevaluate even if only the object reference changed, not the actual name string inside it. But conversely, and this is the tricky part, if you mutate the user object directly, say current user.name Bob, and then user.set current user, where current user is the same object reference, the username computed signal doesn't reevaluate even though the name did change because the signal's reference didn't change.
Ooh, that's a classic gotcha. So how do you solve that specific problem?
You provide a custom equality function directly to the computed options. This function defines exactly how to compare the values. For example, equal A user B user,
Right.
A.name equals B name for a username computed signal derived from a user object. This ensures the computed signal reevaluates only when the actual data of interest, the name, changes, regardless of whether the object reference changed or was mutated. It allows you to fine-tune the memorization behavior for your specific data structures.
Got it. What about minimizing computations themselves, beyond just clever memorization or avoiding dependencies?
Beyond dependencies and memorization, you should also aim to reduce complexity by simplifying the logic within the computed signal itself. Maybe break down large, complex calculations into smaller, more manageable computed signals that chain together. Also, just generally, avoid unnecessary computations. Only perform the calculations that are truly needed within the compute function. Simple but effective hygiene.
The sources also mention batching updates with transaction and using untracked. How do those fit into optimization, especially if you're making multiple signal changes maybe close together?
Right, these are important tools. If you're updating multiple signals that a computed signal depends on simultaneously, using transaction signal1.set new value 1, signal2.set new value 1 is incredibly useful. It ensures the computed signal is reevaluated only once after all the updates inside the transaction have completed. This prevents multiple, potentially redundant reevaluations, which can be a significant performance win if you have complex dependency chains.
Okay, so it bundles them up. And untracked?
Untracked allows you to access a signal's value without creating a dependency. So let's say you have a computed signal derived that depends on source, but inside its calculation, you also want to maybe log the value of another signal called control. If you wrap the access like untracked, changes to control won't trigger derives to reevaluate. This is super useful for auxiliary data, debugging, or logging that shouldn't cause recomputation of your primary reactive flow.
That's quite a toolkit for smart derivations and performance. It really shows the depth of thought that has gone into signals to make them both powerful and efficient right out of the box, but also gives us levers to pull when we need more control.
Exactly.
Okay, we've talked a lot about data and derived values flowing reactively through our applications. But, the real world is messy. Our applications don't just crunch numbers. They talk to servers, they update the screen, they log errors, they interact with third-party stuff. How do signals help us manage these side effects without turning our nice reactive code into a tangled mess? This brings us to the world beyond data, effects and side effects.
Right. Effects are indeed a crucial part of the signals ecosystem. They essentially allow us to bridge the reactive world of signals with the imperative world of side effects. They provide a controlled gateway, a specific place for our reactive data to interact with anything outside that pure data flow.
So what exactly counts as a side effect in this context? For a developer listening, what kind of operations fall into that category?
Good question. Side effects are basically any operations that affect the state of the application outside of the immediate scope of a signal's value, or interact with the external environment in some way. This could be anything from manipulating the DOM directly,
Like changing the screen.
or making HTTP requests to a server, writing data to local storage, interacting with a third-party JavaScript library that doesn't understand signals, or even simply logging messages to the console. All of these are considered side effects because they go beyond just calculating a new value based on existing signals.
So their core purpose then is to provide a controlled and predictable way to react to signal changes and perform these necessary side effects. How do you actually create one?
You use the effect function, pretty side effect logic here.
Okay.
And just like computed signals, effects automatically track dependencies. If a signal accessed inside an effect changes, the entire effect function reruns. This makes sure your side effect is always synchronized with the latest reactive state it depends on. You can even have conditional execution within an effect. For instance, you might only update a full name value in local storage when both first name and last name signals have actual values, preventing unnecessary writes on intermediate states.
That seems powerful, but also like something you need to control carefully. What are the important aspects of controlling effect execution that we need to keep in mind?
Right, control is key. First, execution timing. Effects are generally executed after the component's view has been updated. This is important because if you're doing something like DOM manipulation, the effect has access to the latest fully rendered DOM state, preventing issues where you try to manipulate an element that, say, doesn't exist yet or hasn't been rendered with the latest data.
Okay, timing matters. This also sounds like a prime area for avoiding infinite loops. The source puts a big warning on this, and honestly, we've all probably shipped an infinite loop to production at some point, haven't we?
Slight chuckle. Oh, absolutely. We've all been there. It's a major pitfall. If an effect updates a signal that is also a dependency of the same effect, boom, you've got an infinite loop, and it will crash your application faster than you can say Zone.js.
Yeah.
The example effect is a perfect illustration of exactly what not to do. The solution is simple conceptually. Avoid updating signals that are dependencies of the same effect. If you need to derive a new value based on a signal, use computed signals instead. That's what they're for.
Right.
The allow signal writes option for effect does exist, but the sources strongly emphasize using it with extreme caution and only when absolutely necessary because it does not prevent infinite loops if the updated signal is also a dependency. It's truly an escape hatch, not a pattern you should reach for regularly.
Okay, good warning. So effects are for side effects, not for deriving new state or doing calculations on signals. Got it. And what about injector context? Why does that matter for effects?
Effects are created within an injector context, usually tied to a component or a service. This means they can access services and other dependencies through dependency injection, just like components or other services can. This is incredibly convenient for things like making HTTP requests via an injected HTTP client service, for example.
Okay.
And importantly, if an effect is created within a component's injector, it will be automatically destroyed when that component is destroyed. This is great for preventing memory leaks because you don't usually have to manually clean up effects tied to a component's lifecycle. Angular handles it.
But can you manually control an effect's lifecycle if you need to? Like what if I need an effect to persist longer than a component, or I need to clean up some specific resource tied to it?
Yes, you have that precise control. The effect function actually returns something called an effect ref. If you store this reference, for example, const effect ref, you can then later call effectref.destroy to manually stop the effect. This gives you precise lifecycle control when Angular's automatic cleanup isn't sufficient, perhaps for a global effect running in a service that needs to be torn down explicitly at a certain point.
Okay. And how do effects interact with change detection CD strategies like onPush? Does using signals maybe make onPush easier to manage than it used to be?
That's a great point. By default, effects run after every CD cycle that Angular runs, even if their specific dependencies haven't changed. But with onPush CD, which typically only re-renders components when their inputs change or events originate from them, effects associated with that component only run after CD if the component's inputs have changed or an event originated from it. The critical part, though, is that signals automatically detect changes and trigger updates even with onPush, because Angular knows precisely which components use which signal. This means you get the performance benefits of onPush without the historical complexity of ensuring all your data flows are properly detected by Angular's change detector. Signals truly streamline working with onPush, making it much more straightforward. It's a significant performance gain potential.
Preventing memory leaks is a huge concern in web development, especially with long-running single-page apps. How do we ensure we're cleaning up effects properly to avoid those?
This is absolutely vital, yeah. Effects can involve external subscriptions, like from RxJS observables using toObservable, or manually added event listeners that, if not cleaned up, will lead to those insidious memory leaks over time. Angular does offer auto cleanup for effects when their host component or service is destroyed, unless you explicitly set manual cleanup to true in the effect options.
So the default behavior is generally safe, but if I opt out with manual cleanup, I need to be extra careful. What's the most common and recommended way to clean up these external resources within an effect?
The most common and highly recommended way is by returning a cleanup function directly from the effect callback itself.
Yeah.
This cleanup function will be executed automatically when the effect is destroyed or before it re-executes, if its dependencies change.
Oh, okay.
A classic example is with an RxJS subscription effect. Interval 1000.subscribe, return subscription.unsubscribe. If you add a DOM event listener in an effect, the cleanup function should call remove event listener for that specific element and event. This pattern is clean, declarative, and collocates the setup and teardown logic.
And what if I truly need that manual cleanup option? When would I use that?
If you set manual cleanup true in the effects options, then you are explicitly telling Angular, don't worry about cleanup, I got this. You are then responsible for calling the cleanup function when the effect needs to be cleaned up. You'd store the reference to the effect, for example, effect ref is goes up, and then explicitly call this .effectref.destroy in your components and on destroy lifecycle hook, or wherever is appropriate. This is usually for very specific scenarios, like effects that you want to persist across component destructions, or for very fine-grained resource management where the standard lifecycle isn't quite right. Our sources also mentioned DestroyRef as an injectable alternative that provides a similar auto cleanup mechanism tied to a specific context, like a component or service being destroyed, without needing to manually manage the effect reference itself.
Now, a big area where side effects often come into play is DOM manipulation. How are effects and DOM manipulation linked, and when is it actually appropriate to use effects for this kind of thing?
Right. Effects are indeed essential for DOM manipulation that falls outside the typical data flow of an Angular application. They provide a controlled, reactive way to interact directly with the browser's document object model when Angular's powerful templating features aren't quite enough for what you need to do.
Can you give some concrete examples where an effect might be the right tool for DOM manipulation?
Absolutely. Think about updating text content that's not directly bound in a template, perhaps inside a third-party charting library's canvas element. Element.textContent equals this.message signal. Or maybe adding or removing elements dynamically based on a signal's Boolean value, like showing or hiding a custom error message element imperatively.
Okay.
You could even use them for dynamic styling, like changing an element style.color or font size based on isRed and ilarge signals reacting to some state, or for dynamic class binding to add or remove CSS classes in very specific imperative scenarios where Angular's built-in in-class or class.name might not fit perfectly.
What are the key considerations for DOM manipulation when using effects? It sounds like a powerful tool, but one that needs respect.
You're right, it does. You need to be mindful of performance. Direct DOM manipulation can be expensive, so you should avoid unnecessary updates. Understand how it interacts with Angular's change detection cycle. All those signals help manage this reactivity more precisely. And always be cautious about security when injecting user-provided data directly into the DOM to prevent cross-site scripting XSS vulnerabilities. Sanitize inputs.
But are effects always the answer for DOM manipulation? My gut tells me probably not, and the sources mention alternatives.
Good point, and your gut is right. Effects aren't the only or even always the best way for DOM manipulation. For simple updates, template binding is often sufficient and definitely preferred for its declarative nature. Component decorators like at host listener for reacting to DOM events or at host binding for binding host element properties are powerful and declarative Angular features. And directives offer a fantastic way to create reusable encapsulation of DOM logic in a clean, Angular idiomatic way.
So the takeaway is,
The best practice is really to use effects for DOM manipulation sparingly. Think of them as a last resort for complex or isolated DOM manipulations that Angular's built-in tools don't cover elegantly. They are a powerful escape hatch when you need direct control, but should be used thoughtfully, not as your first instinct for interacting with the DOM.
okay, so summarizing the best practices for using effects, what are the absolute key takeaways for any developer jumping into signals and needing to handle side effects?
All right, let's condense it. First, use sparingly. Only when necessary for true side effects. Never for driving values use computed for that. Second, keep simple, focusing on a single clear task per effect. Third, avoid infinite loops. That's crucial, so don't update signals that are dependencies of the same effect. Fourth, clean up your effects meticulously to prevent memory leaks, preferably by returning a cleanup function. Fifth, consider alternatives like computed, template bindings, directives, or decorators before jumping straight to an effect. Sixth, use allow signal writes with extreme caution and only when you've exhausted other options. Seventh, minimize DOM interactions and batch updates. Since DOM operations are expensive, maybe use request animation frame for animations for smooth visual updates. Eighth, generally avoid direct DOM access and prefer Angular's built-in mechanisms where possible. And finally, test your effects rigorously to ensure they work correctly and, just as importantly, clean up properly.
That's a really comprehensive guide to navigating effects safely and effectively. It definitely drives home the idea that while they're powerful, they really need careful handling and consideration.
Absolutely.
We've built the foundational knowledge on signals, understood how they derive smart values, and how they handle side effects. Now let's talk about how signals become true building blocks within your Angular applications, specifically right inside your components. This seems to start with reactive component inputs.
Yes, this is a pretty significant shift from the traditional @input properties that many Angular developers are very used to. We're moving towards these input and model functions, which bring inherent reactivity directly to component inputs, making them signals themselves.
So input is the new signal-aware way to declare inputs. How does it differ in just the basic usage from the old @input decorator?
Instead of writing it input property.type, you now write property input type, or similarly. You import input from @Angular core. And a key change for usage is that in your component's template, you access the input's value by calling it like a function. It immediately makes it visually clear that this is a reactive value you're dealing with.
Okay. What are the immediate benefits of this new approach compared to the traditional @input that we're used to?
The primary benefits are immediate. Built-in reactivity components can auto-update much more efficiently when their input signals change. This leads to simplified change detection, because Angular only needs to check the specific change signals, not necessarily broader component trees, resulting in improved performance by avoiding potentially unnecessary re-renders. And arguably, it provides a clearer data flow that's more explicit about what's reactive coming into the component.
Can you still make inputs required or give them default values, just like you could with @input?
Yes, absolutely. Those common needs are covered. You can use input.requiredType for mandatory inputs, which gives you a compile time check if it's not provided by the parent. Or for optional inputs with a fallback, you use input_type default value. There's even input.alias, another name, for mapping property names, which can be handy for integrating with existing APIs or perhaps external libraries where the property names don't match perfectly.
What if I receive an input signal, but I need to transform its value before displaying it or using it internally? For example, if I receive a name input, but I always want to display it in uppercase or maybe filter a list based on an input search term.
That's a perfect use case for combining an input signal with a computed signal right inside the component. You can declare your input name, input string, and then immediately declare formatted name, computed this.name.uppercase. This formatted name signal will automatically update whenever the name input signal changes, applying your transformation without any manual intervention or lifecycle hooks.
That's clean.
Our sources even provided a more complex example of filtering a list, where a filtered item's computed signal was derived from an item's input signal and a search term input signal, making complex data transformations based on inputs both reactive and efficient.
And model for two-way binding. This sounds like it simplifies what used to be that combination of @input and @output with an event emitter that sometimes felt a bit, I don't know, clunky.
Precisely. Model really simplifies the two-way binding pattern with signals, making it much more intuitive and less code. You declare it in your child component like value, model string, initial value.
Yeah.
Then, in the parents template, you'd bind it using the familiar banana in a box syntax value parent signal. Inside the child components template, you might have something like input value.set, event.target.value. When the input field changes, the value signal is updated directly within the child via set or update, and that change automatically propagates back to the parent signal and parent component. It creates a truly single shared source of truth for that two-way binding.
Okay, that does sound simpler. So for emitting values from a child component back to its parent, we now have output. How does that compare to the traditional event emitter, which is like the standard way?
Right. Well, event emitter is still very much in use and will continue to be the right choice for many event-based patterns. The new output function offers a more lightweight and efficient way for components to emit values and notify other parts of the application about internal events or state changes, especially when dealing purely with signal-based state. You declare it as data process output string, and then emit a value simply with this .dataprocess.emit processed value. It integrates naturally with the signal ecosystem.
Our sources also mention a best practice regarding using signal data as read-only when exposing state changes via outputs. Why is that important, and how does it enforce a cleaner architecture? This feels related to keeping data flow clear.
Yes, this is really about upholding good encapsulation and maintaining that clear, unidirectional data flow. If you were to directly expose a writable signal, the kind you can set or update, as an output property, the parent component could potentially call set or update on it, directly modifying the child's internal state from the outside.
Ah, yeah, that breaks the boundaries.
Exactly. It breaks encapsulation and can make debugging incredibly difficult because state changes can come from unexpected places. The preferred approach, as highlighted by our sources, is to create a private, writable signal inside the child component, like count signal 0, and then expose a read-only version of it publicly using count this.count.asRead-only. The parent component then receives and can react to this read-only signal. The child's internal methods, like increment, would update the private count, and the public read-only count signal would simply reflect that change to the parent without allowing the parent to modify it.
That enforces a much cleaner architecture and mental model. Love it. What if I need to integrate signals with existing RxJS code? Because, let's face it, RxJS is still a cornerstone of many Angular applications.
That's a very common scenario, and there's a clean solution to observable. It does exactly what it sounds like. It converts a signal into an RxJS observable. This is incredibly useful when you need to integrate signals with existing RxJS-based code or libraries, allowing you to smoothly transition data between the two reactive paradigms. So if you have a count signal, you can easily create count dollars to observable, .count, and then use count with any RxJS operator like debounce time or pipe it into existing RxJS streams. It really bridges the gap seamlessly, giving you the flexibility to use the back tool for the job.
Okay, cool. Finally, let's talk about component state management with Signal itself, beyond just inputs and outputs. How do components use signals just to manage their own isolated internal state?
Components can use Signal to manage their own internal state very effectively and predictably. For a simple counter example, you just have count signal 0 as a component property, and then methods like increment pat value plus 1. The component's template would simply display, and it would react automatically whenever increment is called. Super simple.
And for complex state updates involving arrays or objects within the component state, we're back to that crucial distinction between set, update, and mutate, aren't we?
Yes, it applies just as much to internal component state. Remember, set new value overwrites completely with a new reference, ideal for simple value replacements or complete array object replacements using immutable patterns like .array new item. Update fn modifies based on the previous value, like incrementing a count, by providing a function that takes the current value and returns the new one. And mutate, mutation fn, modifies in place, meaning you directly alter the contents of the object or array within the signal.
Right.
While mutate can be particularly important for complex data structures like arrays or objects where creating a new copy could be inefficient due to deep cloning costs, our sources again reiterate caution about its use due to potential predictability and debugging challenges down the line. For a to-do list inside a component, maybe add todo uses update with immutable array spreading, while update todo might use mutate to just flip a completed flag on a specific item within the array, if and only if the performance of an immutable update, creating a new array with the one modified item, was actually measured and found to be a bottleneck. Always profile before reaching for mutate.
It really sounds like inputs, outputs, and internal signals all come together beautifully to manage a component's state comprehensively and reactively.
Precisely. Input signals provide initial or parent-provided reactive state. Output signals, preferably exposing read-only signals, notify parents of changes, and internal signals manage the component's dynamic behavior. They all leverage the power of reactive signals to create robust, efficient, and responsive UI components.
Okay, that gives us a really clear picture of how signals work within individual components. But applications are rarely just isolated components, right? They need to share data, communicate across different parts of the application, sometimes parts that aren't directly related. So let's move on to orchestrating data flow, sharing signals.
Indeed. We've briefly touched on parent-child communication with input and output signals, but let's recap and maybe dive a bit deeper into some of the nuances there, especially around best practices. Input signals are undeniably the primary and most idiomatic way for parents to pass reactive data down to children.
So if a parent has a username signal, it just passes it like username to a child component, and the child declares username input string or input.required string. The child then accesses it as username. That's pretty straightforward. It maintains that typical Angular property binding flow.
It is. And for more advanced scenarios, remember, the child can further transform input signals using computed signals internally. For example, a child could receive that username input and then create formatted username computed this.username.uppercase. This means the child can react to changes in the input and apply its own specific formatting or business logic reactively, without needing extra methods or lifecycle hooks. It's a powerful pattern for building reusable components that can adapt intelligently to their inputs.
Then there are output signals for children to emit values or notify parents about events back up the chain. The sources point out the event emitter approach using as output, which is familiar territory for most Angular devs, but it also mentions potentially emitting a signal directly, which it explicitly says is less preferred for unidirectional data flow. Can you clarify that? This feels like a common point of confusion when new patterns emerge like this.
Yes, this is a really crucial clarification and touches on a key design principle in component architecture. While a child could technically receive a writable signal directly from the parent, maybe via an add input, and then set or update it from within the child, directly modifying the parent's state.
Yeah, that sounds messy.
It does. The sources strongly emphasize that this can make debugging more difficult and is generally less preferred than using add output with event emitter or the new output function for a clearer unidirectional data flow. The standard recommended Angular pattern still favors events flowing up from child to parent and properties or input signals flowing down from parent to child. This maintains a predictable and much more easily debuggable application structure. Think of outputs as notifications or events, not as mechanisms for direct state manipulation of the parent.
That makes perfect sense. Stick to the established flow for clarity. But what about when components aren't directly parent-child related? They're siblings or cousins or just in totally different parts of the app. This is where shared services come in, right? Acting as that central hub for state that many components might need to access.
This is absolutely the go-to approach for managing application-wide state or even just feature-specific state that needs to be accessed by multiple, unrelated components. A service provides a centralized way to manage and share signals across multiple components, ensuring a single source of truth for that shared piece of data. No more prop drilling through layers of components.
Our sources give a great basic example with a theme service. How would that work in practice to illustrate the concept?
Yeah, it's a classic. Imagine a theme service that holds a signal, like theme, signal, like dark light, and maybe a toggle theme method that just flips the value using update. Component 1, maybe a header component, injects this service, and when a button is clicked, it calls themeservice.toggleTheme. Simultaneously, component 2, maybe a sidebar, also injects theme service and simply displays the theme in its template using themeservice.theme.
Okay.
This setup clearly demonstrates how multiple, otherwise unrelated components can easily react to a single source of truth managed by a service. The theme changes in the service, and both components update automatically because they're consuming the theme signal. It ensures consistency throughout the application, regardless of the component hierarchy.
Now, when sharing signals like this, especially in larger applications, we need to think carefully about performance considerations. What are the key points here to ensure we're not inadvertently creating bottlenecks, even with signals?
Right, even with signals, good hygiene matters. First, reduce unnecessary input changes. You should ensure that input signals passed down to your child components change only when truly necessary. This means avoiding passing completely new object or array references on every change detection cycle if the underlying data hasn't actually changed, as this can still trigger unnecessary work in the child component, even with signal's fine-grained nature. Be mindful of reference changes.
So don't just create new objects or arrays willy-nilly in the parent if the core data is fundamentally the same. Got it.
Exactly. Second, optimize event handlers if they update shared signals. If an event handler updates a signal, especially one that might fire very frequently, like a mouse move or scroll handler updating a shared state, consider debalancing or throttling the updates to avoid excessive change detection cycles across the application. While effects using toObservable are often where you implement this, the principle applies even to raw signal updates triggered by frequent user input if they impact shared state. Third, kind of related to the first point, avoid unnecessary signal updates in general. Only update signals when the data has actually changed. You can use comparison functions like the equal option in signal or computed, or just a simple if check before a calling set, particularly for complex objects, to prevent redundant updates when the new value is effectively the same as the old one. Don't notify if nothing changed.
And finally, a point we've heard before, but it seems extra important for shared state: leveraging memoization with computed signals.
This is absolutely critical for performance in shared state scenarios. Remember, computed signals naturally memoize. This means if their dependencies, which might be other signals in the shared service, haven't changed, they return the cached value instantly, avoiding potentially expensive recomputation. This is incredibly important when you have complex derivations happening in a shared service that multiple components might depend on. If your shared service has a total price computed signal derived from many item signals, and only one item quantity signal changes, only the parts of the calculation chain affected by that one item need to rerun, thanks to memoization and fine-grained tracking. It keeps the impact localized.
So whether it's parent-child communication using inputs and outputs carefully, or using shared services for broader state, the underlying principles of smart signal usage and optimization really remain the same. Minimize unnecessary work, keep data flow clear, and leverage the built-in efficiencies like memoization.
You got it. That's the core idea.
This is the deep dive, and we're not just scratching the surface, we're going deep. So let's really dig into the performance deep dive: optimizing signal applications. While signals inherently bring huge performance gains by design compared to older models, it's still crucial to understand where potential performance bottlenecks can still arise in signal-based applications because, no tool is a complete silver bullet.
You're absolutely right. Even with Angular's fantastic fine-grained reactivity, issues can definitely creep in if you're not mindful. One major area to watch is excessive computations. Remember, computed signals recalculate whenever their dependencies change. If the logic inside a computed signal is very complex, or if its dependencies change extremely frequently, this can still become a performance hit.
Can you give an example?
Sure. Imagine a complex shopping cart total calculation. Maybe you have hundreds of items, and each item has signals for quantity, price, maybe complex discounts. If any single quantity changes, the entire total might need to be recalculated. If that total involves very complex tax rules or shipping logic executed inside the computed function, it could become computationally expensive, especially if changes happen rapidly.
Okay, complex computed signals under high-frequency changes. What else? Unnecessary effects. I remember a time when an accidental runaway effect could just bring my browser to its knees.
Laughs slightly. We've definitely all been there with that one. Effects are powerful, but if they're triggered too often or performing expensive operations inside their callback, they will absolutely degrade performance. A good example would be an effect that logs every single change to a highly active, complex user profile object stored in signals. If that profile has many different signals updating constantly due to user interaction or background processes, the logging effect could be triggered repeatedly, maybe overwhelming the console, causing rendering jank, and generally just slowing down the whole application.
And even with signals simplifying things, there's still some level of change detection overhead, though I know signals aim to minimize this drastically.
Right. While signals are designed to reduce this overhead dramatically by being so precise, frequent signal updates occurring in a very short period can still trigger multiple CD cycles unnecessarily, if not managed. Think about updating a mouse position signal on every single mouse move event. Even if your UI only needs to visually update, say, every 100 meters, continuously updating the signal on every pixel moved can cause excessive rapid-fire change detection cycles and potentially trigger re-renders that aren't actually visible or necessary to the user, consuming valuable CPU cycles for no real benefit.
Okay, so those are the potential problem areas. How do we tackle these bottlenecks? What are the practical strategies for performance tuning we can employ in a signal-based application?
Well, the first one, as we mentioned, is largely built in and a huge benefit: memoization and caching. Computed signals already do this automatically for derived values, giving you a massive win right out of the box. For expensive functions that live outside a computed signal, maybe helpers or utility functions called from multiple places, you might need to implement explicit memoization yourself, perhaps using a simple map to cache results based on input arguments if the function is pure.
Then we have debouncing and throttling. These are pretty familiar concepts in performance optimization, especially from the RxJS world. How do they apply effectively with signals?
Indeed, their purpose is the same: to limit the rate at which a function, or in effect reacting to a signal, is executed. Debouncing executes the function only after a certain period of inactivity. The classic example is a search bar input. The actual search API call only runs after the user stops typing for, say, 300 milliseconds. Throttling ensures a function executes at most once, within a set time period. Think of handling window resize events. You might only update the layout calculation every 100 milliseconds, not continuously as the user drags the window border.
And how do you implement that with signals?
You often implement this by converting the frequently changing signal to an RxJS observable, using toObservable, and then applying standard RxJS operators like debounce time or throttle time before subscribing, perhaps within an effect. The sources showed an example using debounce time on a debounce search term .asObservable. It's a common pattern.
Okay. And selective updates. This sounds like just straightforward common sense optimization, maybe easy to forget.
It is, but surprisingly often overlooked in the heat of development. The principle here is simple: avoid updating signals unnecessarily. Only update if the value actually changed. A simple check like if username.get, username.set before calling set can prevent a whole cascade of downstream computations or effects runs if the value hasn't genuinely changed. Saves work.
What about structuring state, particularly the idea of normalization? This sounds like it could be a pretty significant architectural decision for complex state.
It absolutely can be, and it's very powerful for performance in complex cases. This addresses the problem we touched on earlier: having large, deeply nested objects held within a single signal. If you have one huge user signal containing everything about the user, including a deeply nested address object, and you only change the city within that address.
Right, you have to replace the whole user object reference.
Exactly. You have to replace the entire user object reference when calling set to ensure the signal's reference changes and Angular detects the update. This then triggers updates for anything dependent on that top-level user signal, even components that only care about the user's name, not their city. The solution is to normalize the state by creating separate signals for each property, or for smaller, more focused sub-objects. Instead of one monolithic user signal, you might have user name, user email, user street, user city, etc., all as separate signals, perhaps managed within a service. Updating user city then only affects that specific signal and its direct dependence, leading to much more localized and efficient updates.
That makes a lot of sense for really granular control and minimizing update scope. And immutable data structures are back on the list again. We talked about them with set and update before. Why revisit them here under performance?
Yes, it's worth reinforcing their benefits specifically for performance. Simplified change detection, because Angular can just do a quick reference comparison instead of deep checking. Predictable state, because state never changes in place, only new states are created, making debugging easier. And often improved performance as a result of these factors. Tools like the immer library, with its produce function, can really help you create new immutable copies efficiently without tedious manual deep cloning, making this pattern much easier to adopt, even for complex nested objects.
Okay. We've also covered this, but it seems to bear repeating for performance tuning. Minimizing dependencies in computed signals.
Always the golden rule: avoid depending on unnecessary signals. Only include signals inside your computed function if their values are truly needed for the calculation you're performing right there. If you're not actually using a signal's value in that specific computation, don't access it with signal name. Doing so will only add an unnecessary trigger for reevaluation when that signal changes. Keep dependencies lean.
And on track, again, this tool seems to keep popping up as surprisingly versatile.
Yes, it's a powerful tool specifically to read a signal's value without creating a dependency. This is extremely useful for things like effects that need to log certain values for debugging, but shouldn't rerun, just because the logged value itself changes. Using untracked inside an effect that logs user activity is a perfect example.
Yeah.
You get the current username for your log message without making the effect dependent on username.
Okay. And finally, the sources mentioned detaching effects and change detection strategies on push. How do these fit in?
Detaching effects is a more advanced technique where you might temporarily prevent an effect from executing if it performs expensive operations that aren't needed at a specific time. For example, maybe updating a complex chart that's not currently visible on the screen. This is usually done by manually destroying the effect reference, using .destroy, and perhaps recreating it later when needed. As for onPush, while signals inherently reduce the need for manual change detection optimization by being so precise, using change detection strategy, onPush on your components can further optimize performance by limiting when the component itself is even checked by Angular's change detector, relying even more purely on the signal graph to drive updates. It's a powerful combination for achieving ultimate, finely tuned performance in large applications.
That's a truly deep dive into optimization strategies. It's clear that while signals simplify many things and offer great baseline performance, understanding these nuances and applying these strategies thoughtfully is key to building truly high-performing large-scale applications.
Absolutely. The tools are there, but knowing how and when to use them makes all the difference.
We've learned so much today exploring the power and potential of Angular signals. But even with great tools like these, there are always, common traps and how to avoid them. Let's make sure we steer clear of these potential pitfalls when we start using signals so our code stays robust, maintainable, and performs well.
Right. The first major one, and it's a very common mistake I see, especially for developers migrating from other reactive paradigms or maybe overusing patterns they know, is over-reliance on effects. This is the pitfall, using effects for tasks that are actually much better handled by computed signals or even just direct signal updates within event handlers. Remember, fundamentally, effects are for side effects, meaning interacting with the outside world, the DOM, servers, local storage, etc.
Okay, so using an effect to simply format a string based on another signal, or maybe do a simple calculation and store it in another signal, that would be bad practice, like effect formatted value.set raw value.affix to.
That's a classic anti-pattern. You're using an effect to derive state, which is not its primary purpose. The solution here is simple and much cleaner. Use a computed signal for derived values. Formatted value signal. Computed. That's what computed is designed for. For simple UI updates triggered by user actions, update the relevant signals directly in your event handlers on click this.count.update CLF +1. Effects are powerful, but they're not for deriving data or general flow control within your reactive graph. Reserve them for those true interactions with external systems or the DOM.
Got it. Next up, the dreaded memory leaks.
Yeah.
The silent killer. This is always a headache for any developer, and with reactivity and subscriptions, it can be even more subtle if you're not careful.
Yeah, this pitfall is basically forgetting to clean up resources that effects might create or subscribe to, things like RxJS observables, obtained via toObservable, manually added DOM event listeners using add event listener, or even things like set interval or WebSocket connections initiated within an effect that are tied to a component's lifecycle. If the component is destroyed, but the effect's cleanup doesn't run properly, these resources can hang around, leading to a memory leak. So what's the solution? How do we ensure proper cleanup, especially given that Angular does some automatic cleanup for effects? The safest and most recommended approach is to always return a cleanup function from the effect callback. This function gets executed automatically by Angular when the effect is destroyed, the example, the component is destroyed, or just before the effect reruns due to a dependency change. For an RxJS subscription, it's the classic return a subscription.unsubscribe. For manual event listener, it would be element.remove event listener. This pattern reliably prevents memory leaks associated with effects.
Okay, always return that cleanup function. The next trap is closely related to that mutate versus set update discussion we had earlier. Mutable data structures, breaking the reactivity chain.
Yes, this is a critical pitfall, and it's a source of many subtle, hard-to-debug reactivity bugs. It's the act of directly modifying objects or arrays held by a signal without creating a new reference. Remember, signals primarily track reference equality by default. If the reference to the object or array doesn't change, the signal might not detect an update. even if the contents of that object or array have been profoundly altered.
Right.
This means your UI won't update, or other computed signals dependent on it won't reevaluate, leading to stale or incorrect data being displayed, even though you thought you updated the data.
So that example, items.push new item, items.set items is bad because you're pushing to the original array, then calling set with the exact same array reference back. The signal's reference never changed, so it detects nothing, even though the array contents are different.
Correct. Or user.name new name, user.set. User is also bad for the same reason, mutating the object directly and then setting the same reference back. The solution is consistent. Always strive to create new objects and arrays when updating a signal's value, especially when using set or update. Use immutable patterns like the spread operator, .current items new item or .current username, not new name, or consider libraries like immer with its produce function to help ensure immutability. This guarantees a new reference is created, reliably triggering the signal updates correctly and predictably. It might feel like slightly more typing initially, but it pays dividends in predictability and debugging later.
Definitely seems worth the effort. And finally, a more general pitfall applicable to many areas of development, but particularly relevant when dealing with new performance-focused features like signals. Over-optimizing prematurely, the temptation of complexity.
Ah yes, the siren song of optimization. This pitfall is basically implementing complex performance optimizations, like intricate custom change detection strategies beyond on-push, or elaborate manual memoization caches before you've actually identified a real, measurable performance bottleneck through profiling. This often leads to wasted development effort, overly complex and hard to understand code, and ironically, can sometimes even introduce new bugs that negate any theoretical performance gains.
So the classic premature optimization is the root of all evil applies here too. Don't try to solve problems you don't demonstrably have yet, or maybe problems that signals already solve quite well for you out of the box. What's the solution then?
Simple. Measure performance before optimizing. Use your browser's profiling tools to pinpoint actual problem areas in your application under realistic conditions. Don't guess, don't assume. And crucially, don't fall into the related trap of sacrificing readability for marginal performance gains. Avoid making your code overly complex or convoluted just to shave off a few milliseconds unless you've proven it's absolutely necessary.
Right.
Prioritize clear, concise code that is easy to understand first and foremost. Readable code is maintainable code. And the beauty of signals is that readable idiomatic signal code is often already very performant due to their design.
Excellent advice for any developer, really. Avoiding these common traps will certainly lead to smoother sailing and more robust, maintainable applications as people adopt signals.
Couldn't agree more.
Wow, what a journey we've been on today. We've covered so much ground exploring Angular signals, starting right from the fundamentals of reactive programming, then diving deep into the core signal API, really understanding how to create, read, and update these powerful reactive primitives using set, update, and yes, even the carefully used mutate. We even got into those important nuances of immutability and figuring out when to use each method.
We then explored the brilliance of computed signals, didn't we? Seeing how they allow you to derive smart, automatically updating values from other signals, complete with that built-in dependency tracking and memoization that handles so much of the heavy lifting for you. We also tackled effects, which are so crucial for managing those necessary side effects like DOM manipulation, API calls, and other external interactions, emphasizing the best practices, and crucially, how to avoid common pitfalls like those dreaded infinite loops and those sneaky memory leaks.
Yeah, definitely covered those. We've also seen how signals seamlessly integrate right into the heart of Angular components, from making inputs truly reactive with input and simplifying two-way binding with model, to using output for emitting values, preferably via read-only signals, and just generally managing internal component state in a clean, reactive way. We then looked at how to orchestrate data flow across the application by sharing signals between components, either through parent-child communication or, more commonly for unrelated components, via shared services, always keeping performance and clear architectural patterns top of mind.
And we didn't shy away from that performance deep dive either. We dissected potential bottlenecks that can still occur even with signals and offer practical strategies like selective updates, state normalization, which is a big one, reinforcing immutable data structures, and leveraging tools like untracked for achieving optimal efficiency when needed. And of course, we made sure to highlight those common traps to avoid, hopefully ensuring your path forward with signals is as smooth and productive as possible.
So what does this all mean for you, the developer listening right now?
Signals are honestly so much more than just a shiny new feature in Angular. They really represent a fundamental shift towards building more efficient, more predictable, and ultimately more maintainable Angular applications. They simplify how we handle reactivity, they drastically reduce boilerplate code, goodbye manual subscriptions, and they truly empower you to build incredibly responsive and dynamic user experiences with less friction and likely fewer bugs along the way.
Absolutely. As Angular continues its evolution, signals are unequivocally poised to become the bedrock, the foundation, of how we think about state management and reactivity in modern web development with Angular. The question isn't just, how will I use signals on my project today? But maybe more profoundly, how will they fundamentally reshape my entire approach to application architecture and problem solving tomorrow? They really offer a simpler, more direct, and often more performant way to embrace the power of reactive programming. We've only really scratched the surface in this deep dive, aiming to provide you with a condensed yet highly informed perspective on Angular signals based on the wealth of information out there. The real learning, as always, comes from actually doing. We strongly encourage you to get your hands dirty, experiment with signals in your own projects, apply the best practices and patterns we discussed today, and maybe even join the vibrant Angular community in discussions and feedback, helping to shape the future of this exciting technology. Until next time on the deep dive, keep exploring, keep learning.